Okay, welcome to Chapter 5 of Pre-Calculus 12. We are, I guess, 1/3 of the way through our trigonometry studies in grade 12. Chapters 4, 5, and 6 are all about trig. In Chapter 5, if you're a graphing type of person, then you will love this chapter, because we'll be doing a whole bunch of graphing. If you're an algebra type of person, well, I'll just say, wait till Chapter 6. Okay? Now, we are going to use quite a bit of stuff we learned from Chapter 4 to help us with Chapter 5. So really, if you didn't do well in Chapter 4, well, I'd strongly advise you to go learn that stuff. Okay? You see this little circle here on this page? Well, I think we saw this in Chapter 4. I hope this is familiar with you. Do you remember how to find the sine value at any given angle? So at any given angle, what is the actual sine value? If you said, oh yeah, I know that y is the sine value, then you are correct. So once again, the y value is sine theta. How about finding the cosine value? Well, that just represents the x coordinate. So x equals to cosine theta. Once again, this was from section, I think it was 4.2. Okay. Well, we're going to use these facts today to help us actually show or calculate, or actually, I guess, graph these functions. We're going to use this idea to find out what the graph of sine and cosine actually look like. So here's investigation number 1. I'm going to ask you to graph y equals to sine theta using the data from above. So the data from above is that unit circle. So notice we've got 0, then pi over 2, then pi, then 3 pi over 2, and 2 pi. And for our vertical axes, I'm going to use 2 units to represent a length of 1. So 1, 2, and of course this will be -1, -2. Okay? Remember, sine theta is represented by all the y values of the coordinates. So y values, these ones, y values, y values, y values, y values, y values. You get the gist. So what I'm going to ask you to do is actually plot all of these y values. Okay? So when it's 0 degrees or 0 radians, the y value or the sine value is 0. Okay? Now look back at the unit circle. At 30 degrees or pi over 6, it's 1/2. Now where is pi over 6 on this little chart? Well, this is pi, and notice there's 1, 2, 3, 4, 5, 6 dashes. So guess what? Each one of these must be pi over 6. This one must be 2 pi over 6. If I simplify that, that becomes pi over 3. 3 pi over 6, well, that's just the same thing as pi over 2. That's why I wrote down pi over 2. 4 pi over 6 is the same thing as 2 pi over 3. And then 5 pi over 6, and that would be 6 pi over 6. Okay? If you want me to keep going, this would be 7 pi over 6. 8 pi over 6 is the next one, but that simplifies to 4 pi over 3. Of course, this is just 9 pi over 6. I'm going to write that up top, actually. 9 pi over 6. And then 10 pi over 6 is 5 pi over 3. And 11 pi over 6. And of course, 2 pi is just 12 pi over 6. Okay? So each of these dashes on the horizontal scale are actually pi over 6 units. So pi over 6 was, I think, 1. And then we keep going back to this. Root 2 over 2 is pi over 4. Now, if you're not too sure what that is, root 2 is about 1.41. Divide that by 2. That's approximately 0.71 as a decimal. So at pi over 4. Now, where's pi over 4? Pi over 4 should be halfway between 0 and pi over 2. So right about here. That's pi over 4. So about 0.7. Yeah. And then how about pi over 3? That's root 3 over 2. That's 1.73 divided by 2. Using your calculator, this decimal is about 0.8, I believe, 6. So we'll do 0.86, and then at pi over 2 it's equal to 1. Okay? And I'm going to ask you to keep plotting the rest. I'm not going to go back and forth. I want you to try this. Plot all the dots and then connect the dots. I'm going to draw in 3 pi over 4 for you. That'll be right about there. 5 pi over 6. I believe it's at 0.5. And at pi it's 0. So I think what you should have got so far is a graph that looks something like this. Okay? Keep going now with values that are after pi. So I'm thinking 7 pi over 6 is negative 1/2. And then 5 pi over 4. So I guess this would be 5 pi over 4 right here. That would be negative root 2 over 2. So that's negative 0.86. Sorry, 0.7 I think. 0.7. Then the cube root, not the cube, the root 3 over 2. That's over here. And then at 3 pi over 2, we see the y value is negative 1. Okay? Dum da dum 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 dum. And then we keep going. 5 pi over 3. That would be negative root 3 over 2, so right about there. We've got, of course, 7 pi over 4. That would be over here right in the middle. And that's 0.7. 11 pi over 6, negative 0.5, and 2. So something like that. Ladies and gentlemen, the sine graph. You can clap your hands now. Yay! Now I'm going to ask you to look at this graph and see if you can actually fill out this information underneath, okay? What's the domain? What's the range? What's the max value? What's the min value? What's the y-intercept? What's the theta intercept? So theta is like the x, okay? X value or theta, same thing. So maybe I can use theta here instead of x, okay? So just write down theta if you want. Same thing, okay? What's the domain here? You could probably say that, hey, in this case, the theta value seems to start at 0 and end at 2 pi. You can definitely say that for this graph right now. For the range, we're looking at the possible y values. So it looks like the largest y value is 1. The smallest one is negative 1. So the range is just y is between negative 1 and 1. What's the maximum value? Well, that helps with the range. It's just the 1. What's the minimum value? Also found in the range, negative 1. How about the y-intercept? Y-intercept. That's where it crosses the y-axis. Yeah, right here. So it looks like it's 0. And our theta intercepts, or our x-intercepts, looks like it occurs at 0, pi, and 2 pi. Okay? Now, this is the general basis of sine. We're going to have you actually memorize this because we're going to use this a lot later on. So memorize how it looks like, these special points, especially these ones here, like 0, 1, 0, negative 1, 0. Okay? Memorize those. All right, turn the page. All right. Yes, you guessed it. Let's graph cosine. Now remember what the cosine values were from that unit circle graph. If you don't remember, we said that in section 4.2. Cosine theta is the x coordinates. So I'm going to use all these x coordinates now. X for cosine. By the way, you don't need to circle them in your notes. Okay? Cosine. I'll just go back and, oops, wrong color for highlighting. I want the yellow one for sine. Okay? So, I want you to do this because you don't want me to do this with me blabbing, blabbing, blabbing. Why don't you go ahead now and try to graph out y equals to cosine x using these values I've highlighted in green. And by the way, let's keep the same scale. I'll use 1 and then 2, negative 1, negative 2. Okay? Alright, check back with me when you're done. Here's the graph of y equals cosine theta. Looks very similar to sine, except it looks like it's been moved a little bit. Nonetheless, what's the domain? Looking at this picture, you guessed it, it's the same as the sine one. What's the range? Yep, the same as sine, between 1 and -1. Maximum value, minimum values, oh, they're the same. The intercepts are a little bit different though. The y-intercept here is equal to 1. That's where it crosses the y-axis, right? And the theta intercepts are also different. They're at pi over 2 and 3 pi over 2. Okay? Now, remember when we talk about sine and cosine and all this trig stuff with the unit circle? We learned in chapter 4 that these angles can go not just from 0 to 2 pi, but even more, right? We can continue going around the unit circle a few more times. Meaning the angles here actually continue further on this way to the right, and also this way to the left. So my question to you now is, what do you think would happen to the graph if we were to extend the graphs of both sine and cosine to the left and to the right? So meaning, what's going on over here? What's going on over there? Okay. Think about the periodic nature, how it rotates and repeats itself. So I hope that you kind of realize that, hey, they get repeated. Right? Remember that idea of the coterminal angles? Even though the angle measures are different, the coterminal nature of the terminal arm is the same. Therefore, the coordinates of x and y are also the same. So really what happens is this. So these graphs, so I'll say the sine and cosine graph, repeat as well. Both to the right and to the left. So, if I did ask you to go ahead and keep going, I guess you get a repeated nature like that, and also over here. Which begs the question, what is the domain then? Is the domain really theta is just between 0 and 2 pi? Because technically now, it looks like this graph goes on forever and ever to the right and to the left. So therefore, the domain's not really that. I lied to you. It's actually all real numbers. And similarly, the intercepts are not just pi over 2 and 3 pi over 2, but if you want to find all intercepts, I think you need to write a general solution. Notice that it looks like it's pi over 2, then 3 pi over 2. Seems like it repeats every pi unit, so I would say it's pi over 2 plus pi n, where n is an integer. Okay. And by the way, we should go back to the sine graph and do the same thing. So let me go back to the first page and you do the same thing now. This really goes on again and again to the left and to the right. So that's right, domain is actually wrong. It's all real numbers. And the idea of the intercepts here looks like they are multiples of pi. So I'll just say all the theta intercepts seem to be pi n. In this case, where n is once again an integer. Okay? Now, this thing goes on and on and on like the Energizer Bunny. The two graphs above, okay, what I did in blue only represent actually one cycle. Okay? But then afterwards I extended it with the red. Both these curves are continuous. They go on forever and ever. They're nice and smooth. They don't break. They have no breaks. And because they go and repeat themselves, we have a special name. We call them periodic. Their wavy nature then lends these graphs to be called periodic functions then, because they repeat themselves. Okay? A few more definitions here that you need to know when we're talking about these trig graphs. The length of the interval of the domain over which a graph repeats itself. So, like taking a look at one cycle. Okay, go back to the picture. One cycle of the graph. Okay, what's the length of one cycle? It seems in this case the length of one cycle would be going from 0 to 2 pi. So the length would be 2 pi. There's a special name for that cycle. That's called the period of the graph. Okay? Once again, it's thought of the horizontal length of one cycle. And I just showed you that this graph has a period of 2 pi. Okay? This is both sine and the cosine graph. If you look back on the first page, sine also has a period of 2 pi. The maximum vertical distance, the graph of a sinusoidal function. Sinusoidal does not just mean sine, it means sine and cosine, okay? All this trig stuff. Now the maximum vertical distance varies above and below that horizontal kind of central axis. So if you look at the graph here for cosine, the central axis, the horizontal central axis seems to be like this x-axis. And then I'm saying that the maximum vertical distance, this distance up here, and then the maximum distance going below down here, that has a special name, okay? And that name is called the amplitude. Okay. And if you look back at your graph, can you tell me the actual amplitude of these graphs? So the distance from the highest point to the horizontal central axis, along with the distance from the lowest point to the horizontal central axis. Both those distances is equal to 1, so the amplitude here is 1. Okay? These are the basic facts that you need to know about the sine and cosine graph. First of all, you need to know how to graph them out. You need to know the domain, range, max-min values, y-intercepts, x-intercepts, this idea of period and how it's a period of 2 pi, and this thing called amplitude, which equals to 1. We're going to now combine this with all that stuff you learned from chapter 1 to show you how to graph out more complicated functions of sine and cosine. So recall how in chapter 1, any function of the form y equals a times f of x, this is where you have the a, that value of a in front, and if you compare that to the regular y equals f of x, meant that we had what type of stretch? If you said vertical, I'm so proud of you, because you still remember. And if you didn't, that's okay. I don't know. The vertical stretch of a factor of a was performed about the x-axis. And what happens if a was less than 0? Well, of course, we had a reflection in the x-axis. Well, this all stays the same when we're talking about sine and cosine functions. So I'd like us to graph out sine x, 2 sine x, and negative 0.5 sine x on these grids. And then we'll also talk about the amplitude of each, the period, the range, the domain. Okay? All right. I'm going to ask you to graph them out. Always graph out the regular one first. 0. And I'm just going to do a rough graph, okay? If you can't do it that fast, that's okay, but, just get the general shape, right? I already told you what the important points are by what I did. The points that are 0, the y values where they're 1, and the y value when it's -1. Get those right. Everything else is just a curve, okay? So that's y equals to sine x, or theta. How about 2 sine x then? Well, this stands for a scale factor of a, and it's a vertical expansion. So take all the y values and double it. 0 doubled is still 0. 1 doubled becomes 2. 0 doubled is 0. -1 doubled is -2. 0 is 0. So the same principles apply. And here's my graph of y equals to sine 2x. How about the third one? Well, look here, the amplitude, sorry, not the amplitude, what am I talking about? The a value, which is the vertical stretch, in this case is half, so this is actually a vertical compression by 1/2. That negative means it's a reflection in the x-axis. So 0, well, that stays 0. But now, instead of 1, it's a half, because it's a vertical compression. But because it's reflected, it's now down here. 0 stays the same. All right. So we'll plot this point and that one. And there we go. The green graph is y equals to -0.5 sine x. Okay. What do you notice about the amplitude, period, domain, and range of each of these graphs? Well, the amplitude seems to have varied, right? It looks like it's 2 for the red one. Looks like it's 1 for the blue one. And it's actually a half for the green one. Okay, we don't worry about the reflection when we talk about the amplitude. The range, of course, also varies, so I will color code these. Seems like it goes from -2 to 2 for the red. The regular one, just -1 to 1. And for the green one, small. Period for all of these. Seems to be 2 pi. And it is 2 pi. And the domain, once again, I know we've only graphed out one cycle, but if I were to do it forever and ever, there would be a whole bunch. So it's all real numbers. Okay? Now, as a summary, therefore, when comparing y equals to a sine theta or y equals to a cosine theta to the regular sine and cosine graphs, what do we have? Well, we have a vertical expansion or compression. I'll just call it a stretch for now, of a factor of a. And by the way, this is the new thing. It also turns out the amplitude is also equal to this value of a. Okay? Now, how about from chapter 1? What do we remember about this when we have a b value in front of the x term? If you remember that this is a horizontal stretch, you are correct. I'd be even more impressed if you can remember what the stretch factor is. It's not b, but it's 1 over b. That's right. The horizontal stuff is always backwards, just to confuse us. Okay? But of course, if b is less than 0, similarly, we have some sort of reflection. But this one is a reflection in the y-axis. Okay? Now, before graphing some of these, let's just quickly review what we know about sine and cos. In both of these graphs, the b value right now, because there's nothing in front of the x, would be equal to 1, right? It's like sine 1x, cosine 1x, okay? What's the period for both of these graphs? Yes, it's 2 pi. Good. So the domain of one cycle, okay, just one cycle, not for everything, but for one cycle, must be between 0 and 2 pi. Okay? Keep that in mind now as we look at what happens when we change the value of b. Example number 2. I'm going to ask you to graph out cosine x. And then on the same grid, I'm going to ask you to graph out y equals cosine 2x and y equals cosine 0.5x. Okay? We're almost done. This should be very similar to what we did before in chapter 1. So if you did well in chapter 1, naturally you should be okay here too. Cosine, of course, starts at 1. Then at pi over 2 goes to 0. At pi becomes negative 1. 3 pi over 2 goes back to 0. 2 pi goes up to 1. So make it curved. Okay, don't draw straight lines. There's y equals cos x. That's one cycle. Okay. Notice that in this case, yeah, I think the period or the cycle is equal to 2 pi. Okay. When I graph out cos 2x, this 2 represents some sort of horizontal what? Is it compression or expansion? Remember, it's opposite, so this is compression by a factor of 1/2. Now think about what happens to my period when I compress it by a factor of 1/2. My period should also shrink. 1/2 times 2 pi just gives us pi. So you think about it. Still starts at 1, but now instead of ending at 2 pi, it ends at pi. Instead of being negative 1 down here at pi, it's now down over here. It's half. So notice I'm shrinking everything. Okay, cutting everything in half. There's one cycle of y equals to cosine 2x. Thirdly, we have cosine 0.5x. You guessed it, this is a horizontal expansion by a factor of what again? Remember, it's always the flip, 1 over 1/2, that's equal to 2. So I guess in this case, my period actually doubles from the original one, okay? From the blue one, not from the red one. And so, looks like it's 4 pi. So I'm still starting at 0, but instead of stopping at 2 pi, I'm stopping at 4 pi. Instead of being at negative 1 at pi, it's now at 2 pi, and everything else in the middle. So you see how I stretch this out? There you go. What do you notice about the amplitude in this case? Well, looks like they're all the same to me. The period, of course, this is where it changes. Period seems to be 2 pi for the original graph. It seems to be just pi for y equals to cos 2x. And it's 4 pi for y equals to cosine 0.5x. Domain, I hope you know I just drew one cycle, but this repeats itself. So remember how it repeats. So the domain here would be, of course, all real numbers. And the range, it looks like that hasn't changed in each of these examples. The range is between 1 and negative 1. So when comparing sine bx or cosine bx to sine x or cosine x, we have what type of stretch in this case? You bet, it's a horizontal stretch of a factor of 1 over b. And it also turns out that the period is also equal to, well, I guess this is the factor, so it's 1 over b times 2 pi, or sometimes people write this as 2 pi over b. That's how you can calculate the period. Okay, I'm going to ask you now to try example number 3. Okay, I'm going to ask you to graph 2 cycles of this graph. Then after that, just find all these things: the amplitude, period, max, min, x-intercepts, y-intercepts, domain, range. Okay? You try this on your own. You gotta try this first on your own. Okay? Then come back and double check your answer with me. All right, begin. Hmm, 0.5 horizontal expansion by a factor of 2. How does that change my period? Well, that just doubles my period. 4 pi. So my graph is pretty wide. Okay. That negative, that must be a reflection in the x-axis because it's in front of the A. Okay. Oh, that 3. That 3 seems to be a vertical expansion by a factor of 3. Okay. Well, that just means my amplitude. Oh, yeah. The amplitude equals to 3. Okay, I got all this stuff now. Alright, let's try to graph this out. I guess maybe I'll just do things one at a time. The blue part, okay? Now, once again, I'm doing it one at a time. If you can combine them together, go right ahead. I'm teaching this for you the first time, so I'm not trying to skip too many steps. Looks like if I want to go to 4 pi, then I start at 0, go up to 1, down to 0, negative 1. You kind of notice that it can be split up into 4 parts, right? Can you see this 4 parts? If I were to draw a box around here, oops. If I were to draw a box, I don't know if you like drawing boxes. This is a box, right? Well, I can cut it in half, cut it in half, cut it in half, and those give me some nice places where I can put those, what I call important points, right? Y equals 0, y equals 1, y equals 0, negative 1, 0. Okay? I'm just going to draw one cycle first. Maybe I should draw 2 cycles. Yeah, I'll just draw 2. Okay? If you're curious about the box, watch what I'm going to do now. I'm going to box this as well from 0 to 4 pi. Cut it in half, cut it in half, cut it in half. So, do it. Here it is. See? Box helps. Erase box. Erase, erase, erase. Erase box. Okay, that's 2 cycles of sine 0.5. I've got this expansion by a factor of 3 vertically, so I guess that goes up 3. 0, down 3, 0. Whee! Woo! Woo! Okay, same thing over here. Whee! Whee! Woo! Woo! And then, of course, the last but not least is the reflection. So instead of being positive 3, now it's down at negative 3. Ooh. Oops, that's not very good. Make it more curvy, Mr. Lee. Ooh. Oh, yeah. Curvy, curvy, curvy. Very, very curvy. Alright. So the red graph is my final answer, y equals to negative 3, sine 0.5x. I found the amplitude, I found the period. The max value, of course, is 3. The min value is negative 3. Your x-intercepts seem to occur at 0, 2 pi, 4 pi, or if I write a formula, it's 2 pi n, where n is an integer, every multiple of 2 pi. And y-intercept is 0. Domain seems to be all real numbers. And the range, how about from negative 3 to 3? Did you get all those? If you did, you're ready.